So YouTube, this is my last video example of graphing limacons that I'm throwing up on the web here, in which we're going to graph a variety that are considered to be convex, okay? So let's recall that when we discuss limacons, we're saying these are functions of the type a plus or minus b times either sine or cosine of theta here. And using what we know about, say, cosine and sine and symmetry, and also kind of basic overall shapes, we can determine the basic shape of this graph and throw together a quick sketch. So what we're going to do first is we're going to type this thing. And recall that when we talk about type, we are going to compare our a value to our b value. So when we look at our A and B ratio here, we say if A to B ratio is less than 1, then what we get here is this looped thing, okay? If we say A over B is equal to 1, then we're ending up here with this heart-shaped thing. We refer to this as a cardioid. Okay, moving down the line, we say dimpled, would be this one right here, and this is going to be true if our A over B ratio is stuck between values 1 and 2, excluding those values. And then we would say, last but not least, if A over B exceeds or is at least equal to 2, then we get a convex limacon here. So using this right here, basically what I want to do is I want to just kind of throw together this graph. I notice that A over B here, this ratio A over B is 5 to 2, which is basically 2.5. And I notice that also exceeds 2. So we say that this is going to be a limacon type, and it's convex. Okay. So our maximum R value, recall that your maximum R value occurs at A plus B, neglecting the signs in front of those. So we say 5 plus 2, we're going to get 7 is our maximum R value. And then we say the number of zeros, using the fact that this is convex and knowing what we know about that basic shape, is that it has 0 zeros, it has none. Okay. So to graph significant points, recall that all limaconic graphs, limacons, they have a period of 2 pi. So we're going to go from angle 0 to 2 pi, and I would encourage going by pi halves increments here, but we say 3 pi halves and then 2 pi. So if we were to plug in 0, let's go ahead and plug in 0 into our function. Recall that when you talk about your unit circle, at least, the cosine at 0 is 1, so we get 5 plus 2 is going to give us 7. We say that pi halves here, at pi halves our cosine value, of course, is 0. So we would get 5 plus 0, which is 0, or sorry, 5. When we say pi, we're going to have a cosine value of negative 1. What this does is going to give us 5 minus 2, which is 3. And then this is going to creep back around because of symmetry. So what we're basically going to do is throw these points up on our polar coordinate axes here, a grid. And then we're going to draw in the basic shape of this. Now, knowing also what we know, that this is a cosine graph, it's going to have symmetry about the x-axis here. And also knowing, because our b value is positive, it's going to kind of open to the right here instead of open to the left. So let's go ahead and put these points on our graph. At 0 radians, we're going to go out 1, 2, 3, 4, 5, and we're going to have to use our imaginations here. 6, 7 would be about this far. When we're at pi halves, we're up 5, so that's going to be here. When we're at pi, we're going to go out 1, 2, 3 units. That's going to be right here. And then 3 pi halves will be down at 5. We'll walk out 5 units in a 3 pi halves direction, and then we're back out to 7 again. So what we get is this thing that is really more opening on the right here, and then it's kind of like circular-ish, but it's kind of flatter on the left side. It's kind of like it just got flattened right there. But that's how you would throw together a quick limacon for something that's convex.